In this video, I want to summarize everything that we've learned about complex numbers here in trigonometry. Okay, so as I've mentioned, most of you were probably introduced to complex numbers prior to trigonometry. We talk about complex numbers in algebra, but here in trigonometry, we went into a lot more detail than what we learned in algebra. So we covered everything that we learned in algebra about complex numbers, but then a lot more. Okay, and so now with everything that we've learned about complex numbers in trigonometry, we have a lot more versatility as far as analyzing expressions and equations for all solutions in terms of any number that exists in mathematics, not just pure real numbers. But really, most importantly, regarding the main purpose of why complex numbers were invented in the first place, we now have the ability to find any even root of a negative number. So minus the square root of minus 4, this is just a principal root symbol, but just in general, we have the ability now to find what numbers, when you square them, do you get minus 4? And the same idea with like the fourth root of minus 16. We now have the ability to answer the question, what numbers, when you take them to the fourth power, do you get minus 16? And again, this is interesting and exciting because you can think about it was this reason here why complex numbers were invented. And now we understand how to use complex numbers to answer questions like this. Okay, now, even though at this point, after we've finished with complex numbers in trigonometry, we do know a lot about complex numbers, there still is a good bit more that we can learn. Okay, like for example, what are exponentials of complex numbers, logarithms of complex numbers in relation to trig functions and inverse trig functions, etc. And so there's going to be a whole nother playlist that it's not posted yet, but it's going to be a playlist on complex analysis where we'll be going through this textbook here. And all we're going to do in this course, in this playlist, is just go into a lot more detail on the full scope of complex numbers. Because the idea is you can think about how, yes, complex numbers might have been invented to answer questions like this, but once they're invented, then you have to treat them like they're any other number and integrate them fully into mathematics. And, understand how they're used, how they're graphed, how their graphs work, how they interact with pure real numbers, how they interact with all of the existing equations that we have, etc., throughout all of the existing mathematics, throughout all of the math that existed before they were invented. So as I've mentioned in previous videos, there's going to be, you can't just invent some numbers and have them only apply for these kinds of situations right here. You invent the numbers to answer questions like this, the complex numbers, but then you have to take everything that comes with it though. So like, yes, we have complex numbers that can answer these questions, but as a result, we know that it also ends up being the case that something like the cube root of 8, which there was no issue before complex numbers, we had no issue here at all. We didn't even have an issue with the cube root of minus 8. Much less the cube root of just positive 8. Before, we could just say this was 2, this was minus 2, no problem. But now we know that if you include complex numbers, that there's actually the nth root of any number, no matter what it is, positive, negative, pure, real, whatever, is going to have 3 roots. So this will have one pure real root, 2, and then there's going to be 2 non-real complex numbers as well. And so that's the idea of, you can see there's these like side effects of inventing complex numbers, right? And that's the idea of what we want to study in complex analysis. We want to get the full scope of working with complex numbers across the board in all of the mathematics that we understand and are familiar with, having studied before complex numbers were invented, right? all of the algebra, logarithms, exponentials, all the trigonometry, graphing. How does complex numbers work with all of that? It's where after we've taken a course like this, we'll be much better equipped to approach any system, any equation, any expression, and understand all of the numbers across the board, imaginary and real, that are associated with that system. Okay, so, but what did we learn here in trigonometry? So if you combine what we learned in algebra with what we learned here in trigonometry about complex numbers, what do we understand at this point? We haven't taken this course yet, but at this point, what have we learned? Okay, well, we learned that this all started, this need for an extra number or more numbers than just the real numbers which exist. You can think about as existing on a line, on the real number line, right? All real numbers exist on this number line that extends infinitely in two directions. Okay, well, there was a problem in that if you had an equation like x squared is equal to -1, okay, with just the real numbers, so, right, the real numbers in these include all those categories of integers, whole numbers, rational numbers, irrational numbers, okay? There's no real number here on the real number line that you can plug in, into this equation, so meaning there's no real number that when you square it, you're going to get -1. And so because of that, in order to solve equations like this, new numbers were invented. In particular, the number I was invented, called this imaginary unit here. This number I was invented. And so what is I? Well, first of all, I is a number, just like any other number. You can think about it kind of like it has a symbol in the same way that pi has a symbol or E has its own symbol. That's kind of how you want to think about it. In particular, when it comes to like if you were adding 1 plus pi, well, you can't combine this anymore, right? This is you can't simplify this anymore if you're going to leave pi like as a symbol. But if you had like -3 pi plus 1 minus 2 pi, then you could simplify this to like that. And then you can't go any further. So that's how you kind of want to think about I. It's not a variable like x, but like it kind of operates like a variable in the sense that you combine like terms, but it's not a variable, it's a number. I is a number, okay? Like pi is a number, like E is a number. Okay, so but what is I though? We know what pi is, we know what E is. Pi is the ratio of the diameter to the circumference of any circle. E is based on it's like a limit of compound interest. Okay, but what is I? Well, I is a number that is defined to be, there's two ways you can look at the definition of I. You can look at it as shown here. It's a number that when you square it, you get -1. Or you can look at it from this perspective as it's the principal square root of -1. And I would say that this definition is a little bit more descriptive in the sense that, when you say that I is a number that when you square it, you get -1, there's no ambiguity in terms of here we have a principal square root, which kind of, you think about that as you return only the positive root, right? I. But this is telling you that I squared is equal to -1, but also minus I squared is equal to -1, right? This is kind of like saying, if you said that the principal root of 4 is 2, okay, but then if you said 2 squared is equal to 4. Well, this kind of tells you, this tells you a little bit more in the sense that we also know that the minus of any number when you square it is going to be the same as the positive of that number when you square it. So, I mean, it doesn't matter. These are both good definitions, but just remember that this definition, you're looking at the principal root, so just plus I, but also minus I when you square it, you're going to get -1 as well, because minus I squared, so the -1 squared is just 1, so you're left with I squared, but I squared is -1. Okay? And so with that, we can state this property here. Okay? So now that we've invented I, we can state this property that so if A is greater than 0, and all that's, they're just saying A is greater than 0 because in that case we're going to have a negative number under a principal square root here. If A could, that's the whole idea, right? They're just saying, look, we're dealing with a negative number under a principal square root, okay? What we can say is that the meaning of this, the meaning of a negative, real number on the real number line under a principal square root, you can say that that's equal to, take out an I and just leave the positive of the positive square root. So like if you had the principal square root of -16, that's equal to, take out an I. Okay. Well, the principal root of 16 is 4, so this is equal to 4I. All right. And so this is really useful because now we can solve any equation that involves a question of like, we can solve not just x squared is equal to -1. We can solve any kind of equation that involves like something squared equal to any negative number. -64, right? You take the square root of both sides, do the square root property, which you do the plus or minus like that. So you're left with, okay, but now we know based on this property here that we've got plus or minus I root 64. Root 64 is 8, so plus or minus 8I. And we just solved this equation. Okay, that's great. And this makes sense because 8 squared is 64. Then I squared is -1, so that's -64. If you have -8 squared, that's going to be +64. But then I squared is -1, so you have -64 again. Awesome. Okay. Now, just note though, however, that this property here is just for square roots, not like fourth roots or sixth roots. This is just for square roots. And so, but now speaking of even roots, not except for the second root, at this point we still have an issue. We still have an issue with that. So you might think that, okay, well, what if we wanted to solve the equation x to the fourth is equal to -16? Okay, well, we take the fourth root of both sides. All right, well, first of all, the property of putting a plus or minus like this, if you think back from algebra, this only applies to square roots. This is the square root property. So we can't necessarily just do that, okay? So we're not going to put the plus or minus. Maybe we could. Let's try it. Let's try it. I guess it would make sense that this plus or minus would apply for like any even root, right? Why is that? Because we know, like, just for example, like +16, 2 to the fourth is +16, and -2 to the fourth is +16, just like 2 squared is +4 and -2 squared is +4. So it's kind of the same idea. So put a plus or minus there, and then maybe we could just do this. Take out an I. Why wouldn't this apply to any even root? Makes sense. Okay, the fourth root of 16 is 2 to the fourth is 16, so plus or minus 2I. That's x. What about this? Well, let's plug these solutions back into the equation. So 2I to the fourth. What is that equal to? That's 2 to the fourth times I to the fourth. Okay, 2 to the fourth is 16. But I to the fourth we know is just 1, okay? And +16 is not equal to -16. So this isn't going to work. And you're going to get the same result if you do -2I to the fourth. And so, no, we can't just say that we can apply the square root property to just any even root. We can't just say that this property here applies to even roots, not just square roots. We've got some unanswered questions still. How do we deal with even roots of negative numbers? Because we know that this issue that we started with of like what is the square root of a negative number, that same problem comes up with any even root of a negative number. It's the exact same idea. Okay, so what do? Well, that's the whole purpose of, you can think about why you extend this imaginary number I, which you can write, as like 4i, like minus 12i. You can multiply it by a real coefficient. We extend this imaginary number here to we don't just call it an imaginary number. We call these new numbers complex numbers. So the new numbers that we're going to invent to answer all these questions, they're going to be called complex numbers. So a complex number you can represent as a z like this. This is like a variable for any general complex number. Okay, and a complex number is equal to, we write it as a plus bi. This is just where a and b are just real numbers, like on the number line, on the real number line, or any real number, positive or negative. And we call a the real part of the complex number and b the imaginary part. Okay, and what we do is we think about how we can, so with real numbers, we could put all real numbers on a number line. That's kind of a way you can model all real numbers. Well, we think about all complex numbers as existing in what's called the complex plane, where this is the imaginary axis and this is the real axis, and we just call this the complex plane C. Okay, and so all complex numbers we think about as existing not on a line but in a plane, and they exist in a plane because for any complex number you're going to have these two kind of independent terms here, in the sense that you'll never be able to simplify any further. If you've got like 5 minus 3i, you'll never be able to simplify this anymore. The I term is in its own unique direction. You can't combine these. So they're like their own independent dimensions. So you represent that in 2 dimensions then in a plane like this. Okay? And the idea is like this is A can be any, so this is like 1, 2, 3, 4, minus 1, minus 2. But this is also just another real number axis. Okay, but this is like, you go like this number here. This is a complex number here. Well, that would be the complex number 2 plus 3i. So this extends from positive to negative infinity. This extends from positive to negative infinity. So A and B can be any number from positive to negative infinity. The real part and the imaginary part can be any real number from positive to negative infinity. Okay, but just the numbers on this axis are associated with the I here. Okay, and so this is a complex number Z. This is just like, this is Z1. There's other complex numbers here. You've got, let's see, you could do, there's another complex number, Z2. So Z1 would be equal to 2 plus 3i, and Z2 would be equal to minus 4 minus 3i. Okay, and so this plane extends infinitely in all of its directions. That's what we know a plane. A plane is like an infinite feature, like a line, and this plane contains all complex numbers. Okay, now something to keep in mind, and this can get confusing, but it's really important to remember this, is that there's going to be, in future conversations you have, or future information you're reading somewhere, there's going to be 2 different contexts in the terms of how you view numbers in mathematics. So in one context, you're going to have the set of all real numbers. So like on the number line, you're just referring to the set of all real numbers, and you're viewing the set of all real numbers as distinct from really a number that has an I in it. Any number that has an I in it, you kind of view real numbers as being in its own separate world from any number that has an I in it. And you typically would call that kind of number an imaginary number. Even if it's a complex number, you kind of call this an imaginary number. Okay, that's going to be one context that you'll be having a conversation in or reading something in. Okay, another context, which would be a context where you're learning about complex numbers. So the context of this video, or the context of the complex analysis course. In that context, what you can notice here from the complex plane is that technically a pure real number, like the number 6, is a complex number. So like the complex plane here really contains all numbers that exist in mathematics, technically, right? In the sense that, again, if we're referring to the real number 6, what we would call the real number 6, or the real number 15, or the real number minus 212. Well, these are just complex numbers with an imaginary part of 0. So what you want to keep in mind is that if you're in a context where you're kind of thinking about all numbers, all potential numbers that could exist, like if you're talking about the fundamental theorem of algebra, the context there is you're thinking about all numbers that could come into play in all of mathematics. Well, then when you hear the term complex number, that's referring to any number. That's referring to, so complex numbers, subsets of complex numbers include real numbers like the number 6. We call those just real numbers, as well as what we would call a non-real complex number. So this, you would call the number, these 6 plus 0i and minus 12 plus 0i and 15 plus 0i, you just call that a real number, or maybe a real complex number. But what you would call something like 3 minus 2i, you call that a non-real complex number. You call this a non-real complex number. And then some more terminology is that if you have a complex number, these are all complex number. Every number that exists in the entire universe of mathematics currently is a complex number. But if you have a complex number that has a zero real part, so in that case you've got something like 15i, we call that a pure imaginary number. Okay, and so it all gets categorized like this. All numbers that exist in mathematics are shown here. All numbers. And all of these numbers are complex numbers. They're all complex numbers. They're all numbers that exist in mathematics are contained in the complex plane. Okay, if you're on the horizontal axis that goes through the origin in the complex plane, then that's a real number because the imaginary part is 0. And here's all the subcategories of real numbers: rational numbers, integers, whole numbers, natural numbers, irrational numbers, right? Now, if you're not a real number, that means you're off the x-axis that goes through the origin in the complex plane, then you're a non-real complex number. That just means that, so real numbers have this b equal to 0. Non-real complex numbers have the b not equal to 0. It doesn't mean that the a is equal, for non-real complex numbers, it doesn't mean that the a is equal to 0. It just means that the b is not equal to 0. But if it is the case that you're a non-real complex number and the a is equal to 0, then that's called a pure imaginary number. Okay? And that's how it all breaks down. Now, however, keep in mind, though, that at least currently in the year 2025, maybe someday this won't be the case anymore, years from now, that there's really going to be two contexts in terms of how you talk about numbers in mathematics. As you're aware of, most of the time, the context is going to be that you're referring to real numbers as in their own category of numbers, and any number that has an I in it is in another category. And you tend to call those imaginary or complex numbers. That's with most casual conversations and really most, for non-math majors, most of the time, you've got these two categories. You've got real numbers, which are just part of the real number line. You call those real numbers, and then you call any number that has an I in it, whether it be a pure imaginary number or just a non-real complex number with the a not equal to 0. You call those imaginary or complex number. That would mean the same thing in that context. But in the context of a course like complex analysis or a problem where you're clearly dealing with solutions that are going to have imaginary components in it, they're going to have I in it, equations with I in it, etc. In that context, then you want to adopt this naming convention here. And so in that case, if you hear the word complex number, you know that includes real numbers as well. That's any number. Okay? So it's important to understand this. Okay? And now with this definition of like these new numbers, kind of extending it past just like a number times I, a real number times I, extending it to where we define all of these new numbers as in this complex plane here, now we have the ability to answer the question of what is okay, well, let's think about solving the equation x to the fourth is equal to minus 16. So we're trying to answer the question. This is kind of confusing because when you take a principal root here, well, how do you interpret the principal fourth root of minus 16? Just kind of ignore for right now. We'll talk about this in the more advanced complex analysis course. Just kind of ignore the idea of a principal root symbol for now. Like principal root means you return the positive. A principal even root, you return the positive. Kind of ignore that for now because it's kind of confusing. But yeah, so we're trying to solve this equation. We're trying to answer the question, what numbers, when you take them to the fourth power, do you get minus 16? Now we can answer that. Before, we couldn't answer it with just like a real number times I. We couldn't answer it. But now we can use a complex number. There's going to be a complex number, a real part plus an imaginary part, to where whenever you take it to the fourth power, you're going to get minus 16. Okay, great. So now what we need to do is we need to kind of study these complex numbers here, understand how they work. Yes, we want to understand how exactly it works to where when you take certain complex numbers to the fourth power, you're going to get minus 16. Of course, that's the whole purpose of this. But we can't just study that in its own, like in its own window. We can't just study, all we're going to study is powers and roots of complex numbers. No, these are these new numbers that are invented. So we need to study them from the ground up as brand new numbers and understand them like they're any other number. Okay? So we're going to start by thinking about, well, how do you add and subtract complex numbers? We're going to start there. Then we're going to talk about how do you multiply and divide them. Then we're going to talk about how do you take powers of them. Then we're going to talk about how do you take roots of them. And then that's where we stopped in trigonometry, but you can go further than that and understand how does their graphs really work? How do they work as functions, logarithms, exponentials? How do they relate to, all of the existing math in general? And again, that's what the complex analysis course is all about. But here in trigonometry, we do go to the point of where we can answer this question here, which is really the main purpose. So it's exciting that we did go this far here in trigonometry. So, okay. First of all, one thing you want to notice here, before we talk about the idea of adding and subtracting complex numbers, is that, so since we're in a plane here, we can think about any complex number as being associated with a vector. So vector algebra comes into play. You can use vector algebra in relation to complex numbers. We can think about if we're going to add Z1 and Z2, we can add them as vectors as well. We can think about that idea, or subtracting them as vectors. So keep in mind that you can represent complex numbers as vectors because they're in this 2D plane. That's just something to note, okay? So, but let's start off with the simplest operation in math, adding and subtracting. How do you add and subtract complex numbers? Well, it's important to note that, so this imaginary number I, you're really going to treat this just like it's any other number. This is a number like any other number in math. So how you add it, how you subtract it, how you combine it with other terms, you can multiply it by both sides of an equation, divide by both sides. You can do whatever you want with this, with a term that contains I, just like it's any other number. And in that same sense, you treat a complex number like 4 plus 3i in the same way. This would be just like if you had 8 minus 2 pi. How would you work with this expression in some sort of equation or something? Well, it is what it is, right? It's these two terms that you can't really combine. They're distinct, but you can still like add 2 pi to both sides. You could do whatever you want with this. You could divide 8 minus 2 pi by both sides. You could do whatever you want. It's important for you to realize that's really how you're going to look at I. It's like any other number. It really is. There's nothing to be worried about when you see a term with an I in it and think, I'm supposed to do something different with this than I would do with another number. Absolutely not. Not at all. The only thing you need to be aware of when it comes to dealing with an I in an equation or in an expression is that you're going to want to make sure that you account for any I's that might be mixed in with some terms before you apply certain properties that you know from like algebra or trigonometry, etc., that you learned before you learned about complex numbers. So we were given one example of this in the trigonometry textbook, in that if we've got something like square root of minus 4 times the square root of minus 8. Okay, well, we learned in algebra before we learned about complex numbers that if you're multiplying any two radicals, and it doesn't have to be square roots, it could be any nth root, but we'll apply this for square roots here, then a property is that you can combine them into one radical this way. Okay, so if we would just go ahead and apply that property here, then we get, okay, minus 4 times minus 8 is positive 32. 32 is 16 times 2. Square root of 16 is 4, so 4 root 2. This is incorrect. The square root of minus 4 times the square root of minus 8, or the principal roots, is not equal to positive 4 root 2. And you can see where the issue came up here. It's what happened is that by combining these this way, we ended up multiplying minus 1 times minus 1, which in the end defeated the whole purpose of why we defined I in the first place. Okay, and so what the textbook told us was that for a case like this, where you're multiplying two radicals, where one or more of them have a negative number in the radical, two square radicals, square roots, you want to first take the I out with this property that we were taught. So now we've accounted for the I that's sort of inherently mixed in here. Since we've done that, now we can go ahead and apply this property. So combining these, we get, all right, I squared is negative 1. And so that's the correct answer to the square root of minus 4 times the square root of minus 8. It's minus 4 root 2. And this idea also applied to if you had something that involved like the square root of m divided by the square root of n. This property, it would be the same idea. You don't want to start combining radicals with negatives underneath until you've accounted for that I, at least square root radicals. And so what you can think about is that this idea here is going to extend to more properties than just these combining square root radical properties. It's going to be a kind of a universal principle you're going to want to adopt involving complex numbers or any scenario that you're considering imaginary or complex numbers. You don't want to start applying properties, combining terms, etc., if you haven't accounted for an I that kind of underlies certain terms. Now, this is a little bit confusing in the sense that in a few minutes, we're going to talk about how if we had something like the cube root of 8, okay, well, we know that there's actually 3 total complex roots. Thinking about complex in terms of the full big picture of complex numbers, it includes all numbers. There's actually 3 complex roots here. The nth root of any number, no matter what it is, has n roots. So 1 is going to be the pure real number, 2. But then there's going to be 2 other numbers that actually have a non-real component. Now, I know this is a little bit confusing because it's still like a principal root symbol, which we know means return the positive root, but so which one of these 3 would be the positive root? Just forget about that for now. That's beyond the scope of, we'll learn more about that in the complex analysis course. Just kind of forget about the idea of a principal root for the moment. Okay, but the point I'm trying to illustrate here, though, is that what if we had the cube root of 8 times the cube root of 27? Okay, well, we know that there's imaginary components in some sense mixed in here, right? We know that there's certain numbers that have imaginary parts where when you cube them, you get 8. So don't we need to account for those first? Kind of like we did here? Well, no, this would be valid just as usual, where you could just go ahead and apply this property. This is correct. And so those nuances of how exactly does it apply to where, when exactly do you need to like take out an I before you apply a property? We're going to learn more about the general scope of this in the complex analysis course. But it's just something to keep in mind that when you're dealing with complex numbers or any form of the number I in an equation, that yes, you can operate with I just like it's any other number, but you are going to have to, in the back of your mind, kind of look out for the idea of you don't want to be combining numbers, applying properties, grouping things together, etc. If you've got some like I that's running around that you haven't accounted for yet, that could present an issue. That's just something to keep in mind, but the full scope of this will be addressed in the complex analysis course. Okay, so, but again, even with that though, it's important to remember that I should not, I in an equation or in an expression or whatever should not intimidate you at all. It's just a number like any other number, and you're going to operate with it like it's any other number. You could treat this like you would if you saw pi in an equation or an expression, or e. You could treat it just like that. You could do anything you want with I. All you do is you just remember that I has the meaning that when you square it, you get -1. Or that the principal root of -1 is equal to I. That's what you keep in mind about I. Okay? So, with that, you can think about that the idea of adding 2 complex numbers is trivial. Because it's like asking us to add 8 plus 2 pi and 4 minus 3 pi. Well, at this point in math, doing this is trivial, right? For if you're watching this video. Okay, 8 plus 4 is 12. 2 minus 3 is -1. Done. That's it. I mean, that's exactly what you would do, but with a complex number, but pi would just be an I. Okay? And same with subtracting. If you had 8 minus 3i minus 6 plus 4i, well, okay, we know this is easy. Just distribute that minus. Okay, 8 plus 6 is 14, minus 3 minus 4 is -7. There you go. That's it. Okay, what about multiplying complex numbers? Well, again, this is still trivial. Okay, we've got 2 complex numbers. This is like z1 times z2. This a plus bi times c plus di. I'm saying it's trivial because it's like asking, what would you do if you had 3 minus 2 pi times 6 plus pi? How would you multiply that? Well, okay, we just distribute. 6 times 3 is 18 plus 3 pi minus 12 pi minus 2 pi squared. Okay, 18, 3 pi minus 12 pi is minus 9 pi minus 2 pi squared. And we'd be done here if in the case of pi, but the only difference is with a complex number, we think about how that the meaning of I, that I squared is equal to negative 1. We just keep that in mind. So that means that any expression that we're ever dealing with where we have a power of I, that's an integer power of I that's greater than 1, or that's really anything other than 1, even if you had I to the minus 2, that would still just be 1 over I squared, which would be 1 over negative 1. So anytime you have a power of I, let's just talk about integer powers. That's all we really focused on in trigonometry. An integer power of I other than 1, you can always simplify it because I squared is equal to negative 1. So you should never have a final simplified expression involving I with a power other than 1, some integer power other than 1. You should never, because you can always simplify that. And so, okay, if this was, let's see, if this was 5 minus 2I times minus 3 plus I, okay, well, 5 times 3 is minus 15, plus 5I, plus 6I, minus 2I squared, minus 15, plus 5I, plus 6I is 11I. I squared is negative 1, so this is plus 2. Minus 15 plus 2 is minus 13, and there you go, okay? Now, when it comes to dividing complex numbers, it's not quite as trivial and straightforward because, so if we want to divide the complex numbers 5 minus 3I and 2 plus 4I, okay, well, you can see, like, when it came to multiplication, we just, like, we distributed, right? And it was easy. Well, here, it doesn't work out that way. There's no, we can't really do anything with this with the typical methods we're familiar with. Like, we can't separate this up into two separate fractions, right? Because we have these two terms in the denominator. And so, but it's not a big deal. All we're going to do is we're going to take advantage of the fact that if you multiply two complex conjugates, where complex conjugates are, you've got A plus BI, and the conjugate of that's going to be A minus BI. You just change the sign in the middle. That's it. You don't touch the sign out front of the A. All you do is change the sign between the real part and the imaginary part. That's it. If you multiply two complex conjugates, you end up with a single real number, pure real number. And so we take advantage of that because we can multiply this by 1 in the form of the complex conjugate of the denominator. And what happens is we're gonna do complex number multiplication in the numerator. So 10 minus 20I minus 6I plus 12I squared. So that's going to be, let's see, 10 minus 12, so minus 2 minus 26I is going to be the final result. Minus 2 minus 26I in the numerator. And then in the denominator, we're just going to have a real number. It's going to be, so 4 minus 8I plus 8I is 0. Then minus 16I squared. Well, I squared is negative 1, so that's 4 plus 16 is 20. Now we can separate this up into two separate fractions, which creates that standard form of a complex number. So we've got, and therefore the final result is minus 1/10 minus 13/10 I. And that's a new complex number. The idea is when we're adding, subtracting, multiplying, and dividing complex numbers, the final result we want to be a complex number in standard form like this, the A plus BI standard form. Okay, now, the next thing we talked about was that we know that, so we've got the complex plane with all complex numbers. Okay, all complex numbers are in this single plane here. And the most common way that we identify any number is we put a coordinate system at the middle here. We put a rectangular coordinate system. Okay, with the real part, the imaginary part, and the standard form is any complex number in the complex plane is, well, we'll do it like we could say x plus yi with those rectangular coordinates, right? That's the most common way you identify complex numbers in the complex plane. But it's important to remember that the coordinate system is not married to the complex plane. Like this is all complex numbers. It's just a plane. We add the coordinate system, okay? So what we want to do is we want to think about that. Let's represent complex numbers in a different coordinate system, in particular a polar coordinate system. So instead of an XY coordinate system, what we can do is we can use a polar coordinate system, which the two parameters, right? It's two-dimensional, so you're always going to have to identify all points in 2D space. You're going to need two parameters, okay? And with rectangular, it was x and y. Well, with polar, it's going to be r and theta. Theta is measured from this positive horizontal direction here. Okay, you get r just comes out to some radial point. So this is r, and this is theta. Okay, theta can be any real number technically, like it could be negative, it could be go past 360, but in general, to represent all complex numbers in the complex plane, r could technically be negative, but like really just thinking about to represent all complex numbers, r is just anything greater than 0 to infinity, and theta is anything from 0 to 360 or 0 to 2 pi. But mathematically, you could use angles greater than 360 or negative angles or negative values for r. So if you have like theta is equal to 30 degrees in a negative r, then you would be like, if you just go the other direction of 30, would be the idea. Okay? And so with this, we can say that, so here's a complex number, z, right? And we can think about it as having a vector as well, just like with the rectangular coordinate system, okay? But what's important to remember, though, is that if we put in the background a rectangular coordinate system, what's important to remember is that we're changing the form of how we represent a complex number in terms of the coordinate system, but we're still dealing with the exact same complex number in 3D space. So, okay, since we've got, all right, x is going to be, there's x, there's y. X is going to be r cosine theta. Y is going to be r sine theta. And so what we end up with is that, so we take any complex number in the complex plane, okay? So we're dealing with the same complex number. That is equal to, you could say, x plus yi. That's the rectangular form. That is equal to, these are all equal to, you could say, r times cosine theta plus I sine theta. Because you have the x component is r cosine theta, the y component is r sine theta, and we just factor out an r. Okay, and so these are just two different forms that you can use to represent the same complex number. All right, and again, in general, notice that r is always going to be positive, okay? And this is always going to be positive as well, because the angle, you might say, well, what if you have an angle like that's in the negative y direction? The negative is going to be taken care of with the theta, because if the theta is in the third or fourth quadrant, it's going to make sine of theta negative. So in general, this is always positive for polar form. Kind of like this is always positive as well. The y is going to take care of it. If the y is negative, it'll make this negative. Okay, and so why do we want to do this, though? Why do we want to represent complex numbers in a polar form like this? Well, it's going to be very beneficial, and for a lot of circumstances, if you start with a complex number, which in most cases you'll have it in rectangular form, right? That's going to be the most common way you use it. it's going to be extremely beneficial if you're trying to do something with this, like take a power of this or take a root or find a root of this, right? That's really what we're trying to do, find roots of complex numbers. It's going to be extremely beneficial to first convert this to polar form, then do the operation, get the answer, then convert it back. Okay, and so what do I mean by that? Well, okay, let's first think about how we would multiply numbers, complex numbers in polar form. Now, admittedly, this was not that difficult in rectangular form, but still, let's take a look. If we were multiplying two complex numbers in polar form, how would that work? Well, so we're going to multiply this complex number by this complex number. What the result is, the radius is going to be R1 times R2, and then the resulting angle is just going to be theta 1 plus theta 2. Now, that's pretty easy. Okay, now they represent this in this cis form. This cis theta just means cosine theta, that's the C, plus I, there's the I, sine theta. And so in polar form, you just put the radius out front. And so that's like a compact form of polar form. Okay, but that's pretty easy when it comes to multiplying in polar form. You just multiply the two radiuses and then add the two angles and you're done. Okay, what about dividing in polar form? Well, all you're going to do is divide the two radiuses and subtract the two angles. Now, that's pretty easy as well. Okay, what about powers of complex numbers? So like if we wanted to find a plus bi to the fifth power. Well, we know how to do this mechanically. If we were going to do it in this rectangular form, we know how to multiply complex numbers, but you know, it's just kind of could be a pain, right? That the fifth power is a lot. Maybe we could use the binomial theorem. Yeah, we could do that. But still, you know, this is definitely not the easiest thing to do here. Okay, well, what if we first converted this a plus bi to polar form and then did it? How would that work? Well, that would work out great, because if you have any polar form of a complex number to the nth power, any n, you just do r to the n, and then that's going to be the radius of the final answer, and then the angle is going to be n theta. And this makes sense because you're just multiplying the complex number by itself n times, and so it's just r to the n, and then the angle is just, you add the angle to itself n times, which is n theta. So you can get the answer and then just convert this back to rectangular form. You start with a rectangular form usually to the nth power, convert that rectangular form to polar, do the power, convert it back, and you're done. Okay, but now what about roots of complex numbers? This is really the main heart of what this is all about, right? Well, with polar form, it's going to make roots significantly easier to deal with. Okay, and so the idea of a root of a complex number is that, so if you take any complex number and you raise it to like the nth root, the third root, the fourth root, whatever, and we know how to evaluate this. This is just a power, right? And you get some other number, other complex number. Well, that means that a plus bi is an nth root of x plus yi. That's what it means. Okay, and what we know is that as a result of complex numbers, of how they're defined, that the nth root of any number in mathematics, so any complex number, pure real number, or has an imaginary component, whatever, any number, it could be the nth root of negative 16. It could be the nth root of 81, whatever. Then the result is that there's going to be n complex roots. So those roots might be pure real, they might be pure imaginary, they might have imaginary and real parts, but there's going to be n roots every time. Okay, so just to be clear, if you were finding the cube root of 8, you would technically look at this as you're finding the cube root of 8 plus 0i, this complex number. And there's going to be, yes, we know one of these is going to be 2, but really that's 2 plus 0i, and there's going to be 2 more that are going to have imaginary parts, because we know there's no other pure real number that you cube it and you get 8. But there's going to be 2 more. So you're going to have some other complex numbers that when you cube them, you're going to also get just 8. Okay, so how do you find the roots of any complex number, or just, which means just any number in general? Okay, well, you use this nth root theorem, and just like with powers, it's you want to first convert your number to polar form, the complex number to polar form. Okay, then from there, so we're trying to find the nth root here of this, just r cosine theta plus I sine theta. So this is going to have n separate roots, right? Each of the radiuses are going to be the exact same. It's going to be the, so if this here, if you started with r equal to 8 and you were trying to find the cube root, well, then the r's of the three complex roots are going to all be 2. You take the cube root of 8. They're all going to be 2. That's the idea. So like it's the nth root of r is going to be the radius of each of those. Okay, and so if we think about the final answer of these roots in the complex plane, so if we plotted all of the roots in the complex plane, what that means is that they're going to all be on the same circle with radius equal to the nth root of the radius of the number you're trying to find the roots of, right? This nth root of r is going to be the radius. They're all going to be on a circle like this. Okay? Now, so they all have the same radius, but they're obviously different complex numbers, so that must mean that they're going to have different angles. So what are those angles going to be? Well, all you're going to do is, so we represent the angles with alpha. So you're going to have alpha 1, alpha 2, alpha 3, all the way to alpha n. All you're going to do is you say alpha is equal to, and you put the angle, so you say the angle in the original number that you're taking the root of, okay, plus either 360 or 2 pi times some positive or negative integer k, and then you divide that by n. Okay, now, so technically k could be any integer, positive or negative, but we only want to look at the k's that are going to result in an angle between 0 and 360, because the complex plane it's all the complex numbers are just in a single plane. So there's no reason to look at like the angle 270 as well as the angle that's coterminal with 270, because that's going to be the same complex number. So we want to find distinct complex numbers. So we just want to see for what values of k do we get these unique angles alpha between 0 and 360. And so the way that's going to work is all you're going to need to do is start at k, like the k values you're going to plug in to get an alpha. Start at k is equal to 0, then go up there, then go to 1, 2, etc., 3, until you have n separate k's. So if n was 3, you'd stop at 2. If n was 5, you'd stop at 0, 1, 2, you stop at 4. And then you plug those k's in and you get these n separate alphas, and that's your alphas. And then that's it. Then you've got your complex numbers. You can then, they're in polar form though, you can convert them back to rectangular form and you're done. Now, and what's interesting though, another property that comes out of this is that, so if you plotted let's say we had 3 separate complex numbers, we're doing the third root. So if you, and let's say, okay, there's one of the angles, then there's another, something like that. It's always going to be the case. So you'd have, that would be Z1, Z2, Z3. It's always going to be the case that the angles between these vectors are going to be exactly the same. They're going to be equally spaced, which means that you can think about how if you're taking the cube root, then since we know there's going to be 3 roots and a full circle is 360, well then divide 360 by 3. That means that the spacing between each of these is going to be 120 degrees. If you had the 4th root, you're finding 4 roots. They're spaced all around 360. Well, 360 divided by 4 is 90. So those 4 roots are going to be, the angles are going to be spaced 90 degrees apart. So really, with that, all you have to do is find the first alpha, plug in 0, get the first alpha. That would be like this value here. That would be alpha 1. And then you automatically know, since you know the number of roots that you have, and you can just divide 360 or 2 pi by that, you know the other spacings then. Okay, and so you can see here's an example of a fourth root, and you can see they're all spaced 9 degrees apart. And so all you have to do is find that first angle, and then you know the rest are 9 degrees apart. Okay, so there's a summary of everything we've learned about complex numbers in trigonometry, which is a good bit. Okay, but there still is more for us to learn, and that's what we'll do in the complex analysis course.